Hi, hello. Welcome back. For today's topic, we will be discussing delta to y and y to delta transformation. Okay, so from the last video, we have discussed how to get the equivalent resistance or the total resistance in a series and a parallel circuit combination. Okay, so we will it is very easy to identify between series and parallel because all you have to do is to check for the current. No, so if the current is passing through the same, if the same current is passing through connected resistors, then we can say that they are connected in series. While if different currents pass through the connection of your resistors, then we have a parallel combination. Okay, so from the last video, we have discussed how to get the total resistance in a series circuit and how to get the equivalent resistance for a parallel circuit. And then we have already discussed equivalent resistances from different points in a circuit. So we combine either resistors in series or resistors in parallel. However, there are certain circuits that it's really very difficult to identify whether they are connected in series or are they connected in parallel. Okay, so especially when we are talking about bridges, okay, or bridge circuits. Okay, so for that, we have here a certain technique or solution, okay, for us to convert a certain type of circuit or a certain configuration to another configuration, whichever will be more easier to identify in a certain circuit. Okay, so we call this topic as the delta to y and y to delta transformation. Because for example, we have a circuit wherein it is given in data, and it will be easier for us if we're going to combine them into a y connection. Then we can convert that delta into y, or vice versa. So usually this is being used in a higher electrical subject, so in a power system or in a generator or a motor system, like that. Okay, three-phase motors, like those things. Okay, so we have here delta to y or y to delta transformation, either way, whichever will make it easier. Okay, so it says here, in solving networks, okay, having considerable number of branches, one sometimes experience great difficulty due to a large number of simultaneous equations that have to be solved. Okay, so it's all right if we just have to last video, we already have tried solving simultaneous problems, or we have already tried solving circuit problems, then using a quadratic equation formula, like that, or we combine different equations. Okay, so however, such complicated network can be simplified by successfully replacing delta meshes by equivalent Y system, or vice versa, whichever is necessary or whichever is applicable in a given circuit configuration. Okay, so we have here this is how this delta, so like delta, it's like in the form of a triangle, right? So we have a symbol for delta, which is in the form of a triangle. So delta, which is sometimes referred to as the change, like that. So this side, we call this as delta connection, and then we call this as Y connection, because it somehow forms a letter Y, like this one, or sometimes this is also called a star connection. So in some other books, you can refer to it as a T connection, like that, or a star connection. Okay, so suppose we are given three resistors. We call that R1, R12, we call this R23, and we call this R31. So I hope you will not memorize this in a such a way that this is always R1 2, because it depends on the references that you are using, because sometimes they tend to name this as RAB like that, or RBC, or RAC like that, or sometimes this resistors becomes R12 and this resistors becomes R23 and this resistor becomes R31. So in some other references, the names or the subscripts, they can be interchanged, okay? But I want you to remember this as depending on their position and not on their names or with corresponding subscript, okay? So suppose we're given three resistors. So this is R12, this is R23, this is R31, connected in the delta fashion. So we have here our delta fashion. It's like it's like a triangle, or the symbol for delta, or the symbol for change. So far as the respective terminals are concerned, these three given resistances can be replaced by the three resistances. So we will call this R1, okay? So we will call this R2, and we will call this R3, okay? So we have to determine their relationship with each other. How are we going to replace this R12, R23, and R31 to its corresponding circuit having a resistance value of R1, R2, and R3? Okay, so these two arrangements will be like the equivalent resistance that we have discussed on the previous video. It says that these two arrangements will be electrically equivalent, okay, if the resistance measured between any pair of terminals is the same in both arrangements. Okay, so it doesn't matter if we will be using the delta or the Y, as long as we are going to make use of their equivalent values or equivalent resistance, the result will always be the same. Okay, so we have here, how are we going to do that? So, we have the delta connection, okay, between terminals 1 and 2. So, we will be calling this as your terminal number 1 and this terminal number 2. Okay, so, what happens here is like we are seeing two parallel paths. Okay, so what are those two parallel paths that we are seeing? So, we are seeing this R12, which is in parallel with the series combination R23 and R31. Okay, so just like what we have discussed in series combination. So we are seeing two parallel paths if we're going to look at terminals 1 and 2, and that is your R12 in parallel with the series combination of R31 and R23. So how do we get the equivalent resistor there, or the equivalent resistance? So since there are just two resistors, we are going to make use of the product over sum. Okay, so we get the product, so that is R12 multiplied by the series combination, so the sum of R23 and R31, divided by the sum of the 3, so that is R12 plus the series combination, which is R23 and R31. Okay, so the Y connection, in the Y connection between terminals 1 and 2, okay, so where is terminals 1 and 2? So we have here your terminal 1 and 2. So as we can see, by looking at this 2, R12 in this manner is simply connected in series. So we can say that the Y connection between terminals 1 and 2 here is simply R1 plus R2. Okay, so since the terminal resistances have to be the same, we can equate them, because we can say that the terminals 1 and 2 in the delta connection must be the same with the terminals 1 and 2 in the Y connection. So equating the two, because we're going to say that they are equal, so that will give us R1 plus R2. We have here this one. So this one is equal to this one. So this in the delta connection equal to this in Y connection. And we're going to repeat that on the same portion. Okay, like for example, between terminals 2 and 3. So where is terminals 2 and 3? So this is your terminals 2 and 3. So this is in parallel. So this R31 here, R23 here, R23 here is in parallel with the series combination of R21 and R12. And at the same time, that is in series combination with your R23 here, like this one. So therefore, that is simply R2 plus R3, and so on. The same is true between R1 and R3. Okay, so then we have here our three combinations, or we have here our three equations. Now, if we're going to subtract 1 from 2, for example, we're going to subtract this 2 from 1. Okay, so what's that? I will show you the first one. If we're going to subtract so if we're going to subtract the second equation from the first equation, so this is our first equation, this is our second equation, and this is our third equation. So let us subtract the second equation from the first equation. That will give us, so subtracting our second equation from the first equation, we have this one. Okay, by subtracting, R2 will be cancelled out. Okay, so that will give us R1 minus R3. And then let us just distribute R12 from R23 and R31. Okay, so no problem because our denominator is the same. So therefore, our denominator will remain as R12 plus R23 plus R31. So the difference now, the difference is equivalent to R1 minus R3. Canceling that out, that will have R12 R31 minus R23 minus R31, having this as the denominator. Okay, so next is, let us add equation number 3 from their difference. So equation number 3, so the difference, this is the difference now. Adding that to equation number 3, like this one, that will give us 2R1. Okay, so R3 will be cancelled out. That will give us 2R1. Adding two similar fractions. So what do we mean by similar fractions? Sharing the same denominator. So this is just a matter of cancellation. Okay, so let us cancel out minus R23 plus R31 and plus R23 plus R31. So this will give us R12 R31, R12, R31. So therefore, we have 2 times R12 and R31. So our 2 here will be cancelled out, giving us the value of R1, which is equal to R12, R31 divided by R12 plus R23 plus R31. Okay, so actually, we got the formula for R1. So given the value of your delta, we can convert that into a value of your Y connection. And R1 is equal to R12 times R31 divided by the sum of the 3 delta resistances. Okay, so what is the, so the same is true with in solving for R2 and R3. You may try that at home, okay? So what I want you to look at here is the pattern. Okay, so we have actually formed a pattern. So if we wanted to solve for R1, okay, assuming their position is the same, okay, so R1 is equal to those two resistances in the delta that has 1 in it. Okay, so you have R12 and R31. Okay, so the remaining other one is the R23. That means the one that has no 1 in it, or the one that is connected to our terminal 1. And in the denominator, this is just equivalent to the sum of the 3 delta resistors. Okay, so if we see this pattern, we can easily identify how to solve for R2 and how to solve for R3. Okay, so let us look at this one. We have now these equations. Okay, so this is how we are going to solve for the y connections coming from the delta connections. So R1 is equal to R12 times R31 divided by the sum of the 3 delta resistors. Look at R2. Okay, R2 is equal to R23 multiplied by R12. Okay, look at the values. So, the two resistors in delta that is connected to terminal 2 or has 2 in it. Okay, so what is the other one remaining? That is R13. So 2 is not connected there. So therefore, it is not considered in solving for the value of R2. And then the sum. Okay, and then finally for R3, this is R31 multiplied by R23. So if we wanted to, for example, it becomes RAB, RBC, or RAC, like that. And then we wanted to solve for RA. So it will become RAB times RAC. Okay, divide by RAB plus RBC plus RAC and so on. So, even though we change the positions in the delta connections, no problem as long as you know where did these equations came from. Okay, so how are we going to remember this now? Okay, so just to keep this in mind, if you wanted, you may derive like what we did, but since this will take you much longer time, all you have to do is just to remember how are we going to convert them. Okay, so how do you remember this, class? So the resistance of each arm of the Y is given by the product of the resistances of the two delta sides that meet at its end. Okay, so that is connected to this end. Anyway, they was named because, for example, this is R12. So why is it called R12? Because it is connected both at point 1 and point 2. Okay, so why is it named as R31? Because it is connected both at point 1 and point 3. So what are the two resistances that is connected at point 1? So that is point R31 and R12. So the resistance of each arm of the Y is given by the product of the resistances of the two delta sides that meet, okay, at its end, divided by the sum of the delta resistances. So that is just how you are going to remember converting from delta to Y. Okay? Now, how about from Y to delta? So from Y to delta, we are given R1 and R2, okay, and R3. So we will be now asked to convert that into R12, into R23, and into R31. So what are we going to do? Okay? So in this case, we are going to, so this is our formulas, okay? So this is our formula. So all you have to do is you're going to multiply, okay, 1 and 2. So this is our 1, this is our 2. No. The previous formula, okay? Going back to the previous formula. This one, this is still equations number 1, number 2, and number 3. Okay. So how are you going to remember them? Okay? So how did we arrive at this formula? Because this is somehow much longer to derive than the other one. But all you have to do is to remember. So this is very simple. So all we have to do is to multiply the first and the second equations, okay? So get the product, multiply 1 and 2, and then multiply 2 and 3, and then multiply 3 and 1. Okay, so the product of equations 1 and 2, the products of equations 2 and 3, and the product of equations 3 and 1, you add them together and then you simplify. Okay, so by doing that, we can arrive at these formulas. Okay, so this time, if we're going to convert Y to delta, the givens are R1, R2, and R3. Okay, so we are asked to solve for R12, R23, and R31. And it is given by the formula. Look, this is very simple. All you have to do is to get the product, okay, of each pair. Okay, so of each, since it has three resistances, so you have three combinations. Okay, so what are those three combinations? You have R1 2, you have R2 3. So you have R1 times R2, you have R2 times R3, you have R3 times R1. Solving for R1 2, R2 3, and R3 1, they have the same numerator. Okay, so from delta to y, we have the same denominator. So this time, from y to delta, we have the same numerator. Okay, but look at the denominator, because it is at the denominator that they will differ. Okay, so if we wanted to solve for R1 2, our denominator is R3. So the one which is missing. So this is R1, R2. What is missing? R3. So that is the one in the denominator. So if we wanted to solve for R2, 3, what is missing? Missing is R1. So divided by R1 here. And finally, for R3, 1, what is missing? R2. So R2 is in the denominator here. Okay? So how are you going to remember that? So the equivalent delta resistance between any two terminals is given by the sum of the Y resistances, okay, between those terminals plus the product of these two Y resistances, okay, divide by the third Y resistance. Okay, so whichever is not in the subscript here. So if it is 1, 2, so the denominator is R3, or that is the opposite. Okay, so if we wanted to solve, for example, okay, let's go back at the figure. For example, we wanted to solve for R1, 2. So this is R1, 2. Okay, so this is R1, 2. So the numerator is R1 times R2, R1 times R3, and R3 times R2. Okay, divided by. So if we wanted to look at R1, 2, this is R1 and this is R2. So what it is in the denominator is the opposite terminal, which is not connected to either R1 and I3, or opposite to I1 and I3, and that is your R3 here. Okay, for example, we wanted to solve for R2 3. So this is your R2 3. So this is between terminals 2 and 3. So you just get the product of the 3. So this is R1 times R2, R2 times R3, and R3 times R1. And then this is the 2 connected. What is the opposite resistors that is not connected to R2 and R3? The opposite is R1. Therefore, the denominator is R1. Like that. The same is true with this R31. Okay, so that is how you remember converting one from the other. So it is really very simple. All you have to do is to be familiar with the delta connection and its equivalent Y transformation. So this can help you in solving problems that is very confusing to see if whether that is in series or in parallel. Okay, so let us have an example. So for example, we have here a circuit. Okay, so find the input resistance of the circuit between points A and B. This one. Okay, so we can easily say that these two are in parallel, right? Because if we have a current flowing here, okay, so if we have a current flowing here, automatically that current will divide. Okay, so that current will divide between point C. So one will go through 4 and the other one will go through 8. So making 4 and 8 parallel. However, we have here 6. So another current will divide here and another current will divide here. So because of this 6 here, it is very difficult for us to create an equation actually. But, okay, if we're going to make this, so because this forms a delta, right? This forms a delta. So if we can only convert this into its Y equivalent circuit, we can easily determine whether it is in parallel or it is in series. But we have to make sure that the delta equivalent here, the 4, 8, or 6, we will be getting the correct equivalent in terms of y connection. So, ma'am, can we also make use of the other half here? This also forms a delta, right? So, it can also be. So, it can either be the upper delta or the lower delta, as long as you will be following those equivalent resistors that we have shown, that I have shown you a while ago. Okay? So, how are we going to solve for this? We always start with a redrawing. Okay? So, let us redraw this. Okay. This is our original circuit. Okay, so it is very difficult. If I have here a current, automatically this will divide. So one will go here and one will go there. So technically, it is very clear that 4 and 8 are in parallel. However, at this point, again, that current will divide. So it will go here and it will go here. Okay, at this point rather, another current will divide. It will go here and it will go here. So the confusing one is this case. Okay, so actually this is the scenario if we have a bridge type circuit. So somehow this is also an example of a bridge circuit. Okay, so what are we going to do with this one? But we can convert this, okay? So we can convert this delta, okay? So a while ago, it may look like that, okay? So this is the node. So it's like I have here. So it's like we have here the node, okay? The combination. So this is your 6, and this is our 4, and this is our 8 here. So it's like your delta combination, and we wanted to convert it into its Y equivalent circuit. So how do we convert that into its Y equivalent circuit? Okay, so we have here your point C. So this is at your point C. Okay, so let's name this as your node N, and then this is still your node E, like this one. So this is still your node E, and this is still our node D. Okay, so in this case, you can follow the formula. Okay, so this is still your 4, and this is still the 8, and this is still the 4. We will just change this into its Y equivalent circuit. So if it is already in its Y equivalent circuit, we find it already easy. Why? Because the current will divide here. So one will go here and one will go here. So what happens is this 2 is in series and this 2 is in series, and the series combination is in parallel. So we can easily distinguish how to get the equivalent resistance of our circuit. So the problem is, how are we going to determine, okay, the values of these resistances here to its equivalent values here? So it's just like we have here your RCE, we have here your RED, and we have here your RCD. And we wanted to solve for RC, we wanted to solve for RE, and we wanted to solve for RD. It's just a different name, but the concept on how you're going to remember the formula, it will just be the same. Okay? So how do we solve for RC? Okay? So your RCN now, okay? So your RCN now is equivalent to the resistors that is connected, okay, divided by the total. So what is the total? The total is 8 plus 6 plus 4. So 8 plus 6 plus 4, that will give us a value of 18. So what is in the denominator? The 2 resistors that is connected at point C. So what are those resistors connected at point C? So that is 4 and 8. So 8 times 4 divided by 18, that will give us 16 all over 9. So the value of your RC here is equivalent to 16 all over 9. Okay? How about the value of your RE here? So your RE here is the same. So the denominator is just the sum of the 3. So it is 18. And the 2 resistors that is connected at point E. So what are the 2 resistors that is connected at point E? So it is 8 and 6. So we have here 8 times 6 divided by 18. That will give you 24 all over 9. Okay? So you may do this in fractions or you may do this in decimal, no problem. Okay? As long as you round it off correctly. Okay? And finally, how do we solve for RD? So RD, the same. They share the same denominator, simply the sum of the 3, and those 2 resistors connected at point D. So what are those 2 resistors connected at point D? So that is 4 and 6. So therefore, we have 4 times 6 divided by 18. And that will give you 12 over 9. So the equivalent resistances now is 16 over 9, 12 over 9, and 24 over 9. So this 3 now is equivalent to the delta values here. But this is much easier to analyze than this one. So this is one good example of a delta to Y conversion. Okay, now, to elaborate further, okay, we can now simplify this one. So this is a series combination. So this is a series combination, and this is also a series combination. And the 2 series combinations here are formed in parallel. Okay? So it's like this one. 12 over 9 is in series with 8. So we have here 12 over 9 plus 8. And they are in parallel with the series combination of 24 over 9 plus 4. So we have here 24 over 9 plus 4. Okay? So, getting the sum, so this is 28 over 3 in parallel with 20 over 3. So, product over sum, so that is 28 over 3 times 20 over 3 divided by 28 over 3 plus 20 over 3. So, that will give you 35 all over 9. Okay? So, 35 over 9. So, that is now, okay, if we're going to redraw, always remember, we still have your 16 over 9 here. So, this is still your 4. This is still your 16 over 9. And now, this is your 35 over 9. So, this is very, very simple. From point A to B, as you can see, same current will flow across them. So, this makes them simply in a series circuit. So, what do? We simply add the 3. So, therefore, adding the 3, that will give us 4. So, the equivalent resistance now across point A and B is equal to 4 plus 16 over 9 plus 35 over 9. So, that will give us a total resistance of 29 over 3 ohms. So, that is how we solve for that. Okay? So, it is very difficult for us to analyze this one. But, if we're going to replace that in this manner, it will just be the same. Okay? So, if we do the one at the bottom, it will be the same. Okay? However, your Y will start here. Okay? So, your Y will start here. And then, you have your 2 nodes here. Okay? So, it will just be the same. Just follow on how you're going to get its equivalent value of resistances. So, this is one good example on the application on how are we going to use the delta to Y connection. Okay? So, let's have another example. Okay, so we have here another example class. So, a network of resistance is formed as follows. Okay? So, A and B is equal to 9. So, this is your A and B. CA is equal to 1.5. And BC is equal to 1. So, they form a delta. Okay? So, this is a delta. And then, at point D, okay, so at point D, AD is equal to 6, BD is equal to 4, and CD is equal to 3. Okay? Forming a Y. Okay? So we have here a delta to Y and a Y to 1 delta and 1 Y. So we are asked to measure the equivalent resistance between A and B. So what is the equivalent resistance between A and B? What is the equivalent resistance between B and C? And what is the equivalent resistance between C and A? Okay. So in this case, again, it will be very difficult for us to analyze, okay, because it is a combination of a delta and a Y resistance, okay, or Y circuit. But if we're going to analyze, okay, we can somewhat, okay, so we can somewhat convert the inner Y, okay, so we can, it's either you convert the outer delta to Y, then you have two Y combinations, okay, like that. So it's like two Y combinations or parallel with each other, or it can also be more easier to analyze if you're going to just convert the inner Y into delta. So it's like you have two deltas that are superimposed with each other. Okay? So how are we going to do that? How are you going to analyze that? How are you going to picture that out? Okay. So I have here an illustration. Okay. So this is my inner Y. Okay? So that is your 6, your 4, and your 3. And I wanted to make that into its equivalent delta. Okay? So this is my point A, this is my point B, and this is my point C. Okay, so how are we going to analyze that? So the numerators are the same. Okay, so the numerators are just the combination of the 3. So we have here 6 times 4, 6 times 3, and 4 times 3. So as you can see, all of the denominators are like that. 6 times 4, 6 times 3, 4 times 3. 6 times 4, 6 times 3, 4 times 3. 6 times 4, 6 times 3, and 4 times 3. They share the same numerators. Okay, let us go to the denominator. We have here RAB. Where is RAB? This is your RAB. Okay, so this is your RAB. So what is in the opposite or not connected to RAB is your R3. So therefore, if we wanted to solve for RAB, our denominator is 3. Okay, so this is your A, this is your B, which is the opposite resistance there, that is 3. That's why our denominator here is 3, getting the value equal to 18 ohms. So therefore, in its delta form, we have here your R18, which is 18 ohms. The same is true with RBC. Where is RBC? This is B and C. Okay, so which is not connected or opposite to B and C? It is 6. So therefore, if we wanted to solve for this RBC here, our denominator is 6. Giving us 9 ohms. And finally, RBC. Where is RBC? This is RAC rather. So this is RAC. So which is not connected across RAC. So the opposite. This is 4. So if we wanted to solve for RAC, this is our RAC. This is equivalent to 4. So we solve for 13.5. So from the Y connection, we have now its equivalent delta. Then we can superimpose that to our circuit. So it's just like we have the first delta, okay, the first delta having the value of 9, having the value of 1.5, and having the value of 1, and then we have another delta. like that. So we have another delta having a value of 18, 13.5, and 9. So this is quite easier to analyze. Why? Because the 9 here and the 18 here forms what? A parallel circuit like this one. The 1.5 here and the 13.5 here forms a parallel circuit like this one. And also, the 9 ohms here and the 1 ohm here forms a parallel circuit like this one. So, these parallel circuits here now can easily be combined, okay? Because there are just two parallel resistors, okay? So, how do you do that? You just combine. So, your RAB now is what? 9 parallel 18, so that is product over sum. Okay, so 9 times 18 divided by 9 plus 18, that will give us 6 ohms. Then we have 1.5 parallel 13.5. So 1.5 times 13.5 divided by 13.5 plus 1.5. That will give you 1.35. Okay, so parallel combination, that the result is always smaller than the smaller value. So 1.35 is smaller than 1.5. 6 is smaller than 9. Okay, so somewhat we know that we are on the right track. Okay, and then finally, 9 parallel 1. So this is 9 times 1 divided by 9 plus 1. So that will give you 0.9. So 0.9 is smaller than 1. Okay, so from this one, okay, from our original figure here, we are down to a what? A delta figure. Okay, but we are asked to solve what are the resistances across A and B. So this A and B first. Okay, so what can you see? You can see two parallel paths. What are those two parallel paths? The 6 ohms and the series combination of 1.35 and 0.92. So let's do that. So for A and B now, it is 6 parallel the series combination of 1.35 plus 9, or 6 times 2.25 divided by 6 plus 2.25. The answer is 1.64. So this is the resistance at certain A and B. So this is now very quite easier to compute rather than the original circuit, the one that we didn't use the Y to delta transformation yet. Okay, then the 2 follows. So what is the resistance between B and C? So if we're going to look at this B and C, so we can also see two parallel combinations. So what are the two parallel combinations? The 0.9 in parallel with the series combinations of 6 and 1.35. So 0.9 parallel with series combination of 1.35 plus 6. So that will give you 0.9 times 7.35 divided by 0.9 plus 7.35. So that will give you 0.8. So 0.8 is smaller than 0.9. So that means our answer is correct. Okay? And then finally, what is the equivalent resistance between A and C? So between A and C, we can see two parallel combinations again. One, the 1.35, and the other one, the series combination of 6 and 0.9. So to solve for that, we have here 1.35 in parallel with 6 plus 0.9. So that is 1.35 times 6.9 is divided by 1.35 plus 6.9. So the equivalent resistance now is 1.13 ohms. Okay, so as you can see, it's now quite easy to solve instead of solving it using the original formula here. Okay, so this is one good example of a Y when converted into data. Okay? So, as we go along with our discussion, you can find out that there are really resistor combinations that is quite difficult to analyze, whether it is series or it is in parallel. So, what do is we have this option. Okay? So, we can make use of the delta to y or the y to delta transformation, whichever is more appropriate in our circuit. Like in our first example, it is we make use of delta to y. Okay? And in the second example, we make use of the y to delta. So it's really up to you to analyze what of the two transformations you're going to make use. Okay? So thank you very much, and I hope you learned something today with our discussion. Okay? And see you in our next video. Okay? Bye!